All right, chemistry, let's take a look at the second part of our video lecture for Chapter 10, Section 3, talking about all the different gas laws. Last time we met, we went through Boyle's Law and Charles' Law and did some sample problems there. We also highlighted the difference between an inverse relationship and a direct relationship and how that looked on a graph. We also tried to really pound through it because we're talking about the kinetic molecular theory. All of our calculations that involve temperature need to be done on the Kelvin scale. But today, I want you to be able to use Gay-Lussac's law to calculate pressure-temperature changes at constant volume, and then use the combined gas law to calculate volume temperature pressure changes. So we're calculating it all, right, because it's a combined gas law. And if you're wondering, what are we combining? The three gas laws that we've introduced so far: Boyle's Law, Charles' Law, and Gay-Lussac's law. Then lastly, we're going to be using Dalton's Law of partial pressures to calculate partial pressures and total pressures. And what we're talking about here is when we have a mixture of gases. If we have three different gases in a volume, there's a total pressure, but then there's going to be a pressure due to each individual type of gas. So pressure is the result of collisions of particles with the walls of the container, and the average kinetic energy of the particles is proportional to that average absolute temperature. And when I say absolute, that's code for the Kelvin scale, kelvins. If the absolute value of the gas of the particles is doubled, that means that their average kinetic energy is doubled, right? So if the average kinetic energy is doubled, that means that they are striking the wall of the container with much more force, and they are either going to increase the volume if it's in a flexible container, or you're going to increase the pressure if the container is not flexible. The internal pressure, I should say. Now, if there is a fixed amount of gas in a container of fixed volume and the collisions have twice as much energy, the pressure will also double, right? Again, that's if we have fixed volume. A fixed volume, the pressure will increase. Now, if we change that so the volume can increase, the volume will increase. Right, here is a type of graph that we've seen before. This is a direct relationship here. We can tell because it has that straight line. It's a relationship between temperature and pressure, even though we haven't talked about temperature and pressure, right? We're about to talk about Gay-Lussac's law. However, notice that this relationship is the type of relationship that we've already seen when talking about Charles's law, which is the relationship between temperature and volume. Now we're talking about temperature and pressure, so this is going to be a different equation and a different law. But again, it is a direct relationship, and so as one increases, the other will increase. As one decreases, the other one will decrease. So this, like I said already, this direct relationship between temperature and pressure is known as Gay-Lussac's law. Gay-Lussac's law states that the pressure of a gas at a constant volume is directly proportional to the absolute value. Again, absolute temperature, again, on the Kelvin scale. That's what absolute temperature means, on the Kelvin scale. Remember, direct proportionality, as one increases, the other one changes in the exact same way. That's why it has a straight line when we look at it as a graph. Now, because the pressure of a gas is proportional to the absolute temperature, the following equation is true for a sample at a constant volume. Pressure is equal to temperature multiplied by a constant. So if I'm going to get all of my terms on one side of the equation, all of a sudden I see this form that's very reminiscent of my Charles' law expression, right, which was V over T is equal to K. Remember, K is a constant. It's just the same number. And this should look similar to Charles's law because Charles's law was a direct relationship, and Gay-Lussac's law is also a direct relationship, so we should see the same setup. The only difference is instead of volume up here on the numerator, it's pressure. So at constant pressure, remember we're talking about a fixed container here. It can't expand, it can't contract. It's a fixed volume, it's constant. We would use the following equation to calculate changes in pressure or temperature using Gay-Lussac's law. Pressure 1 over temperature 1 is equal to pressure 2 over temperature 2.
For a gas maintained at constant volume, the ratio of the pressure of the gas to its absolute temperature is a constant.
Again, reminder, this graph, straight line, direct relationship. As one changes, the other one changes in the exact same way. Let's try a sample problem here. An aerosol can, again, fixed container, right? It's not going to expand or contract. An aerosol can containing gas at 101 kilopascals and 22 degrees Celsius is heated to 55 degrees Celsius. Calculate the pressure in the heated can. Now, before we really get into the calculations, I want to point out that all these temperatures here are in degrees Celsius. And in our definitions, we're talking about compared to absolute temperature. Absolute temperature. These have to be on the Kelvin scale. So we're going to have to convert these degrees Celsius into kelvins. Now remember, it's not that difficult. We take the degrees Celsius, we add 273, and that's the temperature on the Kelvin scale. So 22 degrees Celsius becomes 295 kelvins. 55 degrees Celsius becomes 238 kelvins. Now once I have my temperatures in the appropriate units, now I can plug them in to where they ought to go, right? According to my equation, P1 over T1 is equal to P2 over T2, right? So it would look something like this if I were to plug them in as they are, as is. But I want to solve for P2, so I'm going to have to multiply both sides by 328K. And so when I have that set up, I have 101 kilopascals multiplied by 328K divided by 295K. Again, notice K is on both the numerator and the denominator, so as units, those will cancel out, leaving kPa, kilopascals, as my only unit remaining. And if you remember, kilopascals is a unit of pressure. What are we solving for over here? Pressure. So this number makes sense. Also, another way you can see if this makes sense, remember that Gay-Lussac's law is a direct proportionality. It's a direct relationship. So as one term decreases, the other will decrease in the same way. If one term increases, the other one will increase in the same way. So notice how we have an increase in temperature from 295 to 328. We should see an increase in pressure, right? So if the temperature is going up from 295K to 328K, and I calculated P2, the final pressure, and for some reason I came up with a number less than 101, something should strike out. That's a red flag. Something's wrong here. An increase in temperature should result in an increase in pressure according to Gay-Lussac's law, which is what we're studying, and I'm going to give you questions that show just that. So keep your eyes open. Now, here are the major laws that have to do with gases. Now, we have not gone over Avogadro's law yet. We're actually going to save that for chapter 11, but we are going to go over this, and you can rearrange this in the exact same way you can rearrange Boyle's law. But we have Boyle's law, Charles' law, and Gay-Lussac's law, and so we have inverse relationship up here for Boyle's law, and we have direct relationships for Charles' law and Gay-Lussac's law. So one thing that can be helpful for you to remember, if it's a inverse relationship, we're actually multiplying our terms. If it's a direct relationship, we are actually dividing our terms. That can be a very useful thing for you to remember. Boyle's law, Charles' law, and Gay-Lussac's law can be combined, however, into a single equation that can be used for situations in which temperature, pressure, and volume all vary at the same time. Because we're combining all of these gas laws, we call this the combined gas law. Now, the combined gas law expresses the relationships between pressure, volume, and temperature of a fixed amount of gas, right? So the amount of gas is not changing. If I go back to this table right here, N, remember, N represents the moles of gas present. That is not changing, right? So any change in volume is not going to come from a change in the amount of gas. It's going to come from a change in temperature or pressure. But we're going to use this equation, PV over T is equal to K. Again, K is a constant. So as we change one of these terms, the other terms will have to change in concert with that to make sure that this relationship is correct, right? Because this is equal. This has to be true. Now, in the same way that we saw last time, we can rearrange this to calculate changes in one or more of these values. And it will look like P1V1 over T1 is equal to P2V2 over T2. Remember, the subscripts 1 and 2 represent the two sets of the conditions. In the exact same way, in Charles' law and Gay-Lussac's law, T represents kelvins, right? Kelvin scale, absolute temperature. So if I give you a temperature in degrees Celsius, you have to add 273 to it before we can get going. Now, each of the gas laws can be obtained from the combined gas law when the proper variable is held constant, meaning when in doubt, you can use this equation and plug in all of the other constant values.
The pressure times the volume of container 1 equals the pressure times the volume of container 2. As the container gets smaller, the pressure of the gas increases. As the container gets larger, the pressure of the gas decreases. Volume of container 1 over the temperature of container 1 equals the volume of container 2 over the temperature of container 2. As temperature decreases, the volume of the gas decreases. As temperature increases, the volume of the gas increases. The pressure of container 1 over the temperature of container 1 equals the pressure of container 2 over temperature of container 2. As the temperature decreases, the pressure of the gas decreases. As temperature increases, the pressure of the gas also increases. PV over T of container 1 equals PV over T of container 2. Boyle's law, Charles' law, and Gay-Lussac's law all combine to create the combined gas law.
So let's move on to a sample problem. A helium-filled balloon has a volume of 50.0 liters at 25 degrees Celsius and 1.08 atmospheres of pressure. What will the volume be if we change the pressure to 0.855 atmospheres and 10.0 degrees Celsius? So, look at all these things that we know. Now, we remember that temperature has to be on the Kelvin scale, so we're going to add 273 to both of those degrees Celsius values, and we have 298K and 283K. But we are trying to solve for V2, right? That's the volume of helium after the change has been made. It's the second set of conditions. So, let's rearrange our equation. Again, here's a look at that combined gas law. But we're going to rearrange to solve for V2. Now, don't get nervous about all these different values. You already know what they are, right? They were given to you by the question. All you have to do is plug them in appropriately and chug them with your computer. So let's substitute the values given for P1, T1, and T2 into the equation to obtain the final volume, which is not P2, it's V2. Thank you for typos. But simply plug in 1.08, 50.0, 283, and then divide by 0.855 and 298K. We come up with 60.0 liters of helium. Now we're going to finish up with Dalton's law of partial pressures. Okay, so this is a new law. It is a gas law, but it's not going to be used and integrated in the same way that Boyle's law, Charles' law, Gay-Lussac's law, and the combined gas law can be. But it can be used in larger problems. Now, if you're just listening to the name, Dalton's law of partial pressures, we're calculating pressures here. So if we use a certain number of values to calculate a pressure, we can then use that pressure to substitute in for some other p value in one of the other gas laws. That's true, but we're going to have to do a calculation with Dalton's law and then use the other gas laws, or use the other gas laws, then use Dalton's law. We don't quite plug it in for p the same way we do on the other gas laws. But in 1805, John Dalton showed that a mixture of gases, each gas exerts a certain pressure as if it were alone with no other gases in it. Remember, because these particles are so small, it's actually somewhat rare that they collide with one another. And spread out so much over a large volume because of that expansion. The pressure of each gas in a mixture is called its partial pressure. The total pressure of a mixture of gases is the sum of the partial pressures of the gas. This principle is known as Dalton's law of partial pressures. So, Dalton's law of partial pressures can be represented as such. Pressure total is equal to the pressure of whatever A is, plus the pressure of whatever B is, plus the pressure of whatever C is. And if you have 3 gases mixed together, this is the entire law. If you have 5 gases mixed together, you would have 2 more pressure values in here. So you have 5. No matter how many different types of gases you have, you add together the partial pressures of all those individual gases, add them up, and you get pressure of the total. So Dalton's law of partial pressures is explained by, again, the kinetic molecular theory, which is why we started this chapter with it. All of the gas molecules are moving randomly, and each has an equal chance to collide with the container wall. And they're not going to really interact with one another that much because of their high velocity and the great distance between each particle. Each gas exerts a pressure proportional to the number of molecules in the container as a whole. The presence of the other gas molecules does not change that fact.
Dalton's law states that the sum of the partial pressures of individual gases in a mixture equals the total pressure of the mixture. For example, in this container, we can measure a pressure exerted by the oxygen in the container. If we begin to add nitrogen to the mixture, the pressure begins to rise. When the addition of nitrogen is complete, the partial pressure from the nitrogen plus the partial pressure from the oxygen equals the total pressure of the system.
Now, the last idea we're going to talk about is something that we need in order to really use Dalton's law of partial pressures in the way that we're going to do it in this course. Collecting gases by water displacement. Okay? It's a technique, it's a style. And you guys need to understand what we are saying when we use this in a question. Now, gases produced in a laboratory are often collected over water. That's the term, collected over water. The gas production by the reaction displaces, right? We're producing the gas. That gas is going to displace water in the reaction apparatus or reaction bottle. Dalton's law of partial pressures can be applied here to calculate the pressures of gases collected in this way. Because water molecules at the liquid's surface evaporate and mix with gas molecules, water vapor, like any other gas, exerts a pressure. It does have a little bit of a special name. It's called vapor pressure. So to determine the pressure of a gas inside the collection bottle, you would use the following equation, which is a version of Dalton's law of partial pressures. Now, the total pressure is ATM in atmospheres. The pressure of the atmosphere itself is equal to the pressure of whatever that gas is plus the pressure of the water. Right? This is the vapor pressure. Now, if you raise the bottle until the water levels inside and outside the bottle are the same, that means the total pressure outside and inside the bottle will also be the same. Reading the atmospheric pressure from a barometer and looking up the value for the vapor pressure, right, pressure of H2O, at that temperature in an experiment, or of the experiment in a table, you can calculate the pressure of the gas. And again, you will never have to memorize vapor pressures, right? They will tell you vapor pressures, or they will actually give you a table with vapor pressures in it. So again, this is what the apparatus will look like. We're going to have our reactants over here. They're going to react to form a gas, and all of these, all this portion of the apparatus is sealed so that evolved gas will be pushed through here, right, this tube, as the gas expands, and then down into the it's still going through the tube, but it's going to go up through the water right here. Okay, this is an inverted beaker which has a little bit of water in it already, and so the gas will be pushed through this tube, continually through this tube down that's actually underneath the water and up into the bottle, and now all of the gas that's produced will be trapped in this bottle. But that gas, as it expands, as it takes up this volume, it will push the level of the water already in this bottle down. So let's do a sample problem. Oxygen gas from the decomposition of potassium chlorate was collected by water displacement, right? Collected over water. The barometric pressure and the temperature during the experiment were 731.0 torr and 20.0 degrees Celsius respectively. What was the partial pressure of oxygen collected? Well, we know that the overall pressure is 731.0 torr. We also know that the pressure of this water vapor at this temperature is 17.5 torr. Again, we're just looking this up in a book, right? You'll never have to memorize this stuff. You're just going to have to look this up in a book and then in order to use Dalton's Law of partial pressures. Now, what we don't know is the pressure of the O2 specifically. We know the total pressure and we know the partial pressure of water vapor. So we simply rearrange this equation to solve for pressure of oxygen, right? P sub O2. Then substitute the given values of total pressure and water vapor pressure into the equation. We get 713.5 torr. All right, y'all, that's going to do it for this chapter. I will see you next period.